This is You Talk Too Much. We're at PyCon Japan. It is Friday, September 27th, 2024. This presentation will be given in English. My name is James Powell. If you like this presentation, you can, of course, connect with me on LinkedIn. I'll start with some disclaimers. I have a certain reputation that precedes me. If you have no idea who I am, that's probably for the best. I'm known for giving very complicated talks that nobody can understand. The style in which I give these talks is usually very dense and very fast, with an enormous amount of detail. Unfortunately, this talk is going to be simultaneously interpreted, and it caused the organizers of this fine event great consternation hearing that their interpreters would have to interpret the presentation at the usual speed. Unfortunately, my process is to produce these materials at the very last minute, giving the interpreters very little time in advance to prepare their translations. But I thought about my past work and the previous presentations I've given, and I discovered that irrespective of the gimmick, the fun behind those presentations, the message seems not to have landed. It seems like the code is still the same even after suggesting that we improve certain ways that we use our tools. This talk will refer to previous presentations that I've given, but they are not necessary in order to understand what we'll be speaking about today. Today, we're going to try something very new. We're going to try something very different. It turns out I talk too much. I talk too fast, but if I'm right, my argument will stand for itself. My argument must stand for itself. The code alone will tell the story. The code alone will prove my point. Today, we're going to work through an example from first principles. This will be a mostly complete example, including complete code. We'll try to review every line of the code and provide minimal additional commentary. Our goal is to be able to follow every single point in support of the following thesis. The details matter, but the concepts matter much more. The approach for writing good code is never about meticulous memorization, but instead about judicious understanding. Let's take a look. We'll orientate ourselves around a single motivating example. It will be a specific example, specific enough to prove our point. It will be a real example. But ultimately, it is a very simple example. And the example doesn't matter. We're going to try to build a simple strategy simulator. More specifically, a trading strategy simulator, wherein, given prices, we will derive trades with the goal of generating profits. We will make two simplifying assumptions. We're talking about low-frequency trading, and we want highly flexible strategy definitions. Let's start with something very simple, the data modeling. We're talking about prices and trades. What is a price? On some date, at some time, some asset has some given price. Multiple prices are just a collection of these price data. Naively, we might look at this data and pivot it. And when we pivot it, we might say, this lends itself to pandas, or polars, or DuckDB. But we'll choose pandas for the purpose of this talk. If I were to tell you that pandas is just the data frame with columnar operations like the mean, the standard deviation, the skew, the kurtosis, or KURT for short, if I were to tell you that it's about vectorizing and broadcasting, if I were to share with you details like group by ag, group by transform, group by apply, rolling, and expanding, you would realize the details do matter, but my explanation is completely shallow and meaningless. Unfortunately, most pandas documentation is no less shallow than this. Because, given this explanation, you would naively model the data as follows. One column for date, one column for time, one column for asset, and one column for price. it would look something like this. Let's populate with random data. We'll generate dates for 90 days. We'll generate times from 9 o'clock to about 4:30 on 15-minute intervals. We'll randomly generate 4-letter asset names, and we'll randomly generate prices. These randomly generated prices are meaningless. They won't move like real prices do. We'll take those and collect them into our data frame. But this is wrong. We'll get a value error. And the value error will say, this is columnar data. All arrays must be of the same length. So we'll change our code very slightly. We'll use itertools.product in order to denormalize each one of these columns and produce correct looking data. From this, we'll try to do something with the data. We'll try to compute an end-of-day price. This is a very common thing we might do. We hear about them on the news all the time. We might naively try to group by the date and the asset. Looking at each date and asset individually, we might try to aggregate and sort the values by time, getting the last value. But this is wrong, because .ag does single column computations. So we'll swap out .ag for .apply, and this will work, but it'll be very slow. And ultimately, it's still wrong. We are off to a bad start. This is the bad start that I see many pandas and many Python users get off to. They try to write some code, and it doesn't work. They make a small change, and it starts working, and they say, that's enough, the code works. Instead, we're going to start over. We're going to start over with our code. We're going to start over with our approach. And we're most importantly going to start over with our understanding. The syntax doesn't matter. And pandas doesn't even matter. What matters is, for any sufficiently mature tool, there exists an evolved design such that that evolved design may not be evident. It may not even be documented. The pandas documentation claims that a data frame is two-dimensional. The pandas documentation is wrong. Pandas is one-dimensional. For reference, see my talk at PyData Amsterdam last week. The evolved design is the idea that in the equilibrium of forces controlling the development of this project, there arise constraints that give rise to a design. And if we do not appreciate this design, every attempt at using this tool will be wrong, either wrong on purpose or right by accident. But as an aside, I should note, wrong code can sometimes be useful. Let's start over with pandas. Here is my interpretation of the most important thing about this very common and very useful tool. Pandas is about restricted computation domains and index alignment. Another aside, you don't have to like this talk, but you do need to stop resetting index. If you are a pandas user, do not reset index. You are fighting the tool. That's not how the tool is designed to be used. Because in pandas, we want aligned lookups. We want to use the index. It represents critical metadata. If we look at our pricing information, we can separate the date, time, and asset. That's what we look up, the actual data, the price, by. The date, time, and asset are metadata, and the price is the data. A small note, in pandas, there is no D-type date. There is no D-type time. There is a D-type object. But I mentioned to you the idea of the restricted computation domain. Pure Python has a time type. It has a date type, but pandas does not. If we use D-type object, we are obviating the benefits of pandas itself. Instead, we want to use a datetime64ns, turning our data into something slightly simpler, indexed on the date time and the asset with the data of the price. The code might look like this. We generate dates using a date range. We generate tickers by finding unique 4-letter ticker names. We identify 2 currencies for our example. And we compute a categorical index, taking all of our tickers and our currencies. The use of categorical here is purposeful because When we trade in tickers and currencies, they come from an enumerated finite set of possibilities. They are not arbitrary strings. We might construct our prices like this. Index on the Cartesian product of our dates and our assets and generate moderately meaningful random data by taking a normal distribution as the starting point for each price and computing a product over time, cumulatively multiplying that down our date axis, giving us a simple random walk. As an aside, when we talk about prices, we are talking about a fundamental fiction, a useful fiction. Prices do not actually exist. Just because somebody says they'll buy something at a certain price doesn't mean they actually will. But as a useful fiction, they give us a simple linear relation between the volume of what we trade and the total cash that will change hands. As a consequence, prices are implicitly denominated. Therefore, in our structure, we may want to choose to denominate this in USD, setting the price of $1 to exactly $1. We probably want to set the price of the JPY to whatever the correct exchange rate is, but that's a detail that is not important for this example. We might want to limit ourselves to trading hours. If this is denominated in USD, we might assume the New York Stock Exchange, which is open from 9:30 to 4 p.m. Unfortunately, this code won't work because it turns out pandas has a coherent design but a very inconsistent and incomplete implementation. Therefore, we may need a minor contortion. We'll accomplish the same goal through more steps. The result will look like this. From this, if we want to compute an end-of-day price, we can group by the date level of the index, date value, the asset, looking at only the observed signals that we have, and computing the first and the last value. This will be much faster and is more fluent than what we had before, despite being slightly more code. The result might look like this. Having modeled prices, we might think, how do we model trades? Anytime we start a problem, we should go back to our first principles. Our first principles for pandas are index alignment and the restricted computation domain. When we think about a restricted computation domain, we are thinking about an interpreted view of raw memory, especially if we're talking about the NumPy backend. Machine-typed data, therefore the use of date times 64ns, a 64-bit integer representing the number of nanoseconds since the epoch. We are talking about a fixed-size dynamic shape structure that is storing one-dimensional data, where each series or each column of the data frame is one data set. And that data is either strictly homogeneous or loosely, ambiguously heterogeneous. The latter terminology will only make sense if you refer to the aforementioned PyData Amsterdam talk that I gave last week. When we want to model a trade, we might say a trade is the idea that at some date and time, some asset changed hands in some volume at some price. But there's more than one price. We trade at a certain price, and the market has another price. In this case, we lost money. We traded at a price higher. We purchased at a price higher than what the market would buy it back from us. In this case, we might have made money. Note that prices are unsigned values, but volumes are signed values. A positive volume means we bought something. A negative volume means we sold something. Here's some related terminology. A position is just the sum of all the trades that we performed. It is also signed. A positive position means a long position. This is just terminology. A negative position means a short position. Again, just terminology. The cash that changed hands is just a negative volume times a traded price. If I buy something, I give you cash. If I sell something, you give me cash. The market value is merely what I would get if I liquidated the position today. If I have a long position, I will receive cash by closing out my portfolio. If I have a short position, I will have to pay cash. The profit that we make is merely the sum of these two signed values, the market value and the cash. Therefore, naively, we may choose to model our trades as follows. This code is quite dense, but I'll break it down for you. For every date and every asset, we have 3 chances to trade in that name. We compute our volume by randomly deciding a buy or a sell and some volume from 100 to 100,000 with the limitation in trading in lots of even sizes. We'll sample this to make this data look more realistic. We'll remove anything that happens outside of market hours. We'll look up the actual price and assume we trade exactly at the market maker's price. The data might look like this. But this is wrong. It works, but it's wrong. And you might wonder, why is it wrong? Because in fact, for many of you pandas users, this is how people use pandas. They stack columns onto the end, and they end up with something that quickly becomes untenable. If we think about a slight extension to this problem, we'll see what went wrong. But first, let me show you that this actually works. We can compute our market price by looking up in our prices the dates at a given reference date for each asset. We can compute our cash, our market value, and our profit by following the formula from before. The result looks very much like a typical pandas data frame with extra columns attached to the end. If we want our total profit, we could group by the asset, project the profit column, and compute a sum. And we'll see some mistakes we made in the generation of this data. We shouldn't have a JPY position since we shouldn't be trading directly in these currencies. But that's a trivial mistake. And if we focus on those trivial mistakes, we will miss the more foundational mistake, which is obvious once we extend the problem. Let's assume that we have a two-sided market. When we talk about prices, there's not just one price. In fact, prices don't really exist, but when we pretend they do, there's often 2 sides to the market, a buy price and a sell price. Somebody buys something from you at a different price, then they'll allow you to sell it back to them. If we model our prices as a 2-sided market, then we may change our pricing data very slightly. Instead of being a series, it becomes a data frame with 2 columns, buy and sell. And it looks something like this. Then, when we try to compute our P&L, we may first have to determine the position, because to liquidate the position, we have to know if it's long or short. To get rid of everything that I own, I need to determine the price at which somebody will take it off of my hands. If I have a positive position, I need the sell price. If I have a negative position, I need the buy price. So we need one extra step to compute the cumulative volume. The rest of the analysis appears similar, and the result looks something like this. But this result is subtly and yet completely wrong, because if we sort this in some fashion, the result quickly loses any meaning. If we sort this data, or we sample this data, that position column is going to become meaningless. Because if we think about the columns we've created, the market value is dependent on the volume and the market price by definition. And it's dependent on the same rows, volume and market price, but the position is dependent on the volume for all previous rows. We have made a fundamental error here, mixing deltas and states. The deltas being the trades which changed how much we owned, and the states being the sum of those. Remember, the position is the sum of the trades. We are mixing 2 very different things into a structure that loses its coherence almost immediately. And every subsequent thing we try to do with this structure is going to become harder, more complex, and less tenable. When we started with the prices and trades, we started with a series for the prices and a data frame for the trades. And we changed the prices from a series to a data frame, so let's try changing the trades from a data frame to a series. If we think about a simple trade is an exchange of some ticker for some currency, modeled by the volume of the ticker that I bought or sold and the price at which I bought or sold it. Where a ticker is something like these 2 examples, and a currency, we can all imagine, is something like these 2 examples. These are subsumed under the category of an asset. but what about multi-leg trades? It's often the case that when I am exchanging some ticker for some currency, there may be some intermediary. In the real world, certain commodities like oil cannot be transacted in any arbitrary currency. Therefore, I may need to trade from USD into JPY and then from JPY into the underlying asset that I want to trade. I could try to represent this as a data frame with multiple columns, but the columns of a data frame are not its variable axis. How do I even know how many legs are the most number of legs a trade could have? This is an impossible way for me to represent this data. Instead, what I should do is model my trades as a series object. And I'll model only the volume that changed hands. It would look something like this. From there, I can start to fill in the gaps. I can execute my trades by taking the trades that I have and identifying what the traded price is. Then, computing what the cash that would change hands, because cash is real, and producing another series object. If I concatenate my original trades with the execution of the trades, I go from something that looks like this, some asset changed hands at some date, to something that looks like this, some asset that changed hands, and there's an arbitrary number of additional rows corresponding to the other legs of the trade. Note that the fiction of linear prices can now be removed from our example because we can compute the execution of real cash money that changes hands in any arbitrary way we want. To identify the market value, we can liquidate these trades, which is merely selling everything as of a certain date, defined in terms of execution. Therefore, to see what our market value is, we merely take our trades and liquidate them. Given these trades, we create corresponding netting trades and the cash that would change hands. In these two examples, there's one small detail you may see if you look at the code closely afterwards. The use of an extension to the pandas index registered accessor. Here's what that code looks like. It's not important for the example. From this, we can compute positions by executing the trades and grouping by asset. It looks something like this. We can compute P&L by concatenating the trades, the execution of the trades, and the liquidation of the trades, and it will look something like this. We can even compute our total P&L. We can compute our total P&L by taking the cash flows, combining those with the original cash that changed hands. It will look something like this, and we can do a little bit of pandas tricks to make this look the way we want by adding in another layer to our index to get the traded asset. But foundationally, in this example, a question arises. Who cares? Because many of you aren't even pandas users, and you're not in the finance industry. So why does this example even matter to you? The details of this problem genuinely do not matter. It's not a particularly hard problem, but it shows mistakes that can be made every step along the way, where those mistakes are non-obvious, and yet, the moment we try to extend this problem, the code, the result of those mistakes is obviously wrong. We are lacking in this example principles that guide us to the answer. And it is incumbent upon us that for all of the tools, whether pandas or Python or other tools that we use, we must understand how these tools work at a much deeper level than we may otherwise assume. We must understand them beyond the superficial, ideally through their implicit design to their inherent meaning. When we look at the first principles aren't something that we nod our head and say, yes, yes, sure, 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 and then write any code we want to write. But they are the guiding force for writing any correct code. Every one of the implicit principles that we discover should be a direct guidance to the code we want to write. Because the evolved design confers meaning, and it guides all use. If we stray from it, our code will be wrong. If we hew to it, our code will be right. If we look at the implicit design and the notes that I shared with you, you can see each one of them directly contributed to a mistake that I fixed. Machine typed, used datetime 64NS. One-dimensional, trades are actually ambiguously heterogeneous one-dimensional data. The prices are two data sets, the buy side and the sell side, combined in a single one-dimensional index-aligned structure, the data frame. But there's an important detail here. There were other criteria I mentioned, that NumPy is an interpreted view of raw memory, and that NumPy is fixed size dynamic shape. Because the example is still wrong. Every time we ignore the core principles behind the tools that we use, every time we fail to discover what those principles are, we will write code, and that code will not be correct. Here, in this case, we can try to understand what the gap was. When we talk about a NumPy ND array, in contrast to a Python list, we might say that a NumPy ND array is fixed size but dynamic shape. And yet, a Python list is fixed shape and dynamic size. In other words, for a NumPy ND array, we can reshape it as we please. But for a list, we cannot reshape it. It is always linear, but we can append to it. If we have a trading simulator, this means we have a discrete time simulator. A discrete time simulator is a simulator where, at each time step, we perform some operation. In other words, at each time step, we determine what to trade. If we extend this problem very slightly, we will realize that what we want to do is start with some initial balance and then run through our simulator and identify what other trades you want to perform. But there is no series append method because you cannot grow a pandas series in place. You can't grow a NumPy ND array in place. It's an interpretive view of raw memory. You can't grow it because you don't know what's sitting after it in memory. This is why we might call pandas or NumPy a tail-end analytical tool. In other words, these are tools where we perform some data collection, we perform some other steps, yet more other steps, and at the very end, when all of the data has been collected, we use pandas or NumPy in order to perform analysis. But it would be a shame to throw away all the use of pandas in this particular example, despite knowing that when we try to grow a pandas series or data frame, we must concatenate it, and this will make a copy of the data. This will be very expensive and very slow. Thus, we can extend our example very slightly. Instead of executing a single series worth of trades, we might extend this to operate on a list of series. There is an important subtlety in this code. When we become data science users or machine learning users, we often think we have entered a new world, and we have set the old world behind. Now that I know about NumPy and pandas, I don't need to know about pure Python. And yet, when we look at these tools, we see they coexist in a deliberately designed interplay. Here, we have an example of that interplay. The correct modeling of this would be something that can grow a list within which we have something that can be computed readily, a NumPy, ND array, or a pandas series. And in fact, we'll change our examples to operate using simple Python syntax, like list comprehensions, in order to apply the execution or liquidation operation on each individual entry. There's a small amount of design necessary to get the liquidation to work. We can take it from operating on one series to operating on a list of series and returning a list of liquidation values, or we can embed that into the liquidation helper class. This is a small subtlety. But whatever the case, we'll rewrite our liquidation, and we'll end up with something that is more nearly correct. When we think about these two methods, we might combine them under some structure, a class. For many of you, when you start writing code, if the first thing you do is write a class mimicking something in the real world, you're going down the wrong path. It is typically the case that we want to identify the analytical aspects of our code and then decide how they get grouped together into structures like this structure representing the market itself. Here, we then have the ability to free ourselves from limitations like linear pricing and to implement the model of the simulator however we please. Finally, we might ask ourselves, how does this come together in our simulator? What does our simulator look like? We have a discrete time simulator which means at each step we perform some operation. It is a trading simulator, so at each step we decide what trades we want to perform. We might model it like this: a simulate function that iterates over dates, calling a strategy callback that identifies what trades we want to perform. A strategy might look like this: something that computes the returns given a sample portfolio with a 90-day window, that identifies the n largest, 20th greatest returns, and determines through some balancing mechanism how to trade into those names, returning the trades, the liquidation of those trades, selling out of everything we own, the new trades, and the execution of those trades. Bringing this together, we can start with an initial balance, some cash, and run our simulator. But this is still wrong, because the concepts that we have here are not specific to pandas. And even though it is the motivating example that we're using, understanding the concepts is not something that is limited to the use of these computational tools. In fact, we've made a huge mistake in the modeling of our simulator, ignoring key concepts specific to Python itself, or perhaps even more general than that. The moment we look at that simulator, it should pop into our head: this is a generator coroutine. And if I were to explain to you what a generator or a generator coroutine was, by saying generators are related to collections.abc.iterable. They are related to collections.abc.iterators. They're used for creating iterators. They're about laziness versus eagerness. And generator coroutines are related to async def. They're related to the capital C coroutine in the collections.abc module. They're kind of weird, and we don't know where to use them. Again, this is shallow and meaningless. A discrete time simulator is one in which at each time step we perform some operation. Therefore, it is one computation that has been broken down into parts. One computation is what we call a function, or in other words, a subroutine. And when we break it down into parts, that's what a coroutine is. A generator coroutine is a single computation that has been broken down into parts to accomplish some specific goal. The generator coroutine part merely allows us to take incremental output and feed in incremental input. And I must again share with you, you still do not have to like this talk, but you need to stop writing things that would be obvious generators or generator coroutines. Because when we look at our simulator and we see a for loop here that's looping in some fashion with some ending modality, something that controls how it ends, we should immediately think, run this forever. This is a trivial generator. And if it takes new data, feed that back in using the .send method. When we think about our strategy as a function that computes the next trades, we should think to ourselves, well, does it need history? And if so, where do we store that history? Store it in the instance state of, or in the local state of, the generator coroutine. And in fact, many of the contortions that we see in past presentations around generator coroutines are largely secondary. Likely, a strategy is not just a generator coroutine, but in fact, a pumped generator coroutine to eliminate a first rest modality. It's a small detail that will assist us in use, but we'll never get to that detail if we ignore the core concepts. In fact, most likely, it's not even a pumped generator coroutine. It is an API normalized pumped generator coroutine, another small detail that will evolve out of the constraints of our use, but is largely secondary to the choice of the structure itself. When we do this, we can now model things that were simply intractable before, such as strategies that change their minds midstream. Generator coroutines are probably the best way that we can model anything we call a backtester, a simulator, an agent model in Python. When we talk about the market, should that be a generator coroutine? Probably not by itself. Perhaps the market state is the result of something that is a generator coroutine that yields out the market state. And bringing these together, we can come up with an incredibly general solution for our simulator. We compute a market state with an unpumped generator coroutine. We determine what the initial state is. We run through states forever, asking the strategy to tell us what new trades it wants, accepting those new trades, giving us the flexibility to handle things like slippage or other details of execution risk, and computing the next market state. From here, you can see that there's an implicit decision that was made. When we talk about Python, we are talking about a coherently designed tool. When we talk about Python together with machine learning tools, data science tools like pandas, PyTorch, Polars, Dask, NumPy, any of them, we are talking about a restricted computation domain idea. The idea of a heterogeneous topology, where some of our code is program structure, and some of our code is computation. Pure Python is how we retain the generality that's needed to model what is important to a human being, the flexibility of the strategy. Whereas pandas, or Polars, or NumPy, or Dask, or PyTorch, or CUDA are the constrained means by which we get performance. Therefore, we expect our Python code to be slow, but unconstrained, and our pandas code to be fast and yet constrained. And again, this could be NumPy, this could be Polars, this could be anything. Remember at the beginning of this motivating example, I shared with you some key simplifying assumptions. Low frequency trading with highly flexible strategies. Many of you thought that was not an important consideration, merely a simplifying assumption for the purposes of this example. But it is exactly why we're allowed to do the strategy definition in Python. When we pare things down to the core principles, we will discover that those core principles dictate everything about our problem. When we can see those core principles, we can immediately identify where the insufficient aspects of our code are, where this code will fail to generalize and be extensible to new business requirements. The details at the core do matter. Understanding the syntax of pandas and some of the details of the group by modalities is important for using this tool. Understanding the newest syntax in Python is important for writing code that will actually run. But the concepts always matter more. When you're in a code review and you see a for loop and you tell your colleague that should be a loop comprehension, are you really making a meaningful point, or are you quibbling over something trivial? But when you see a function that should be a generator coroutine, you're going to the core concepts and a gap in core understanding of the problem that might lead to genuinely better code. Honestly, I don't know what more I can say, because I've been telling people about generator coroutines and the details of pandas for years. And yet, it seems like it still is taking a while for people to use these tools better. But hopefully, I can motivate that there is a real design behind these, even if that design was not intentional. And that design informs every single choice we make in our code. It is almost always the case that judicious understanding beats meticulous memorization. That if we understand what we're doing, then we'll be able to use these tools more effectively than if we know the latest features and the latest syntax. I have been saying this for years. I don't know what more I can say. I can say that it's been an absolute pleasure coming here to PyCon Japan in, I believe, its 11th year. I can say thank you to all of the organizers for putting on what is going to be an amazing event. It's been my pleasure to present to all of you. But on this topic, I can encourage you, look for the implicit design. Pandas doesn't matter. If you don't use pandas, this example is not critical for you to understand. But look for the underlying design, the meaning behind your tools, because in that absence, no matter how much you read the documentation, no matter how much you memorize the syntax, your code will be wrong, wrong, wrong. And so, in the end, I'm not sure what else I can say. I think I talk too much. Thank you, everybody.